Okay, so in this video, we're going to take a look at the Leisen Reimer binomial framework that follows Cox-Ross-Rubinstein. Cox-Ross-Rubinstein is probably the more celebrated model, the better established model, the one that appears a bit more in the literature. But Leisen Reimer also very attractive, mainly because it converges quickly, and there is a discussion here around convergence that you might take a look at. So just to get the ball rolling, we have some VBA code here. It's based on Espen-Haug, but I go a little bit further than Espen. I truncate the zero region of the tree, and that's important for Leisen Reimer, right? And I'll leave a link to some deeper explanation of why the zero region in the Leisen Reimer lattice is important. It's a kind of a constant or a static, constant region, very predictable region, and it makes up a substantial component of the binomial lattice. So it does make certain efficiencies available then when we execute. So the big advantage of Espen-Haug design code is that it makes use of dynamic memory. In addition here, we go one step further, we truncate the zero region, and a deeper explanation I leave with a link below. Okay, let's just copy that, right, copy, and then we'll go into Excel. And we have already pasted that function in. So basically the same function appears here, right? So if you take a look, and then we called up the function in the spreadsheet. So just to understand a little bit how we would do that, Leisen Reimer truncate, and then we could come up here and then we could follow the value. So A for American, P for put option, S for the value of the stock, X for the exercise value, T for the time period involved, and then we have risk-free rate is given as 7%, B, the cost of carry is 7, so no dividend yield here, volatility 30%, and the number of steps we're going to use is 25. Now, we have a value here of 7028, right? And that's fine. And we can compare that if we look at the varying in this table 1 here that appears comes from the Leisen Reimer 1996 paper, and they compared the results of different strikes, and then Cox-Ross-Rubinstein, Jarrod, Tian, and we have here Leisen Reimer. There was method 1, method 2, and when we compared result here 7.028, it's consistent with the value that appears here. So we can perhaps round it. 702858, same, and then note that the parameters are the same, right? That the parameters that we have here are also consistent, N25. Okay, so this tree, we can do one more. What if the value then was 90? We have 1233, and for the value of 90 here, we have for the, okay, we have, that's the exercise, so I should have actually changed. If we might note here, that's the strike. So I shouldn't have changed, that's 100. If I went to the value of 90 here, we get 312832. 312832 for an exercise of 90. Okay, so this Leisen-Reimer function is working well, and then we can benchmark and try one other. 80, 1042, 104264, and if the exercise is 120, we have 267576, 267576. Okay, so this code, truncated code, is performing well, right? We've no issues in terms of estimation. American put options.